So what do I mean by saying that this example is very, very good? In general, what is the criteria for an example in mathematics to be very, very good? So in my opinion, there are a couple of criteria. First, this example illustrates some non-triviality in the definition. The definition itself might look simple, but through this example, you will be able to see the definition is not trivial at all. And second, this example will contain some constructions that involves some other theories in mathematics. Say if an example is in topology, but to construct that example, you have to use some algebra, some analysis. That would be a very, very good example. You will learn a lot by understanding that example alone. And thirdly, this example would be great if it is also technical. Why being technical is great? So this is my personal opinion, that to learn math is just not about learning theories. You also want to learn a lot of techniques, because techniques can be highly non-trivial. Like in algebraic topology, I remember, so by theory, the computation of fundamental groups and homology groups are not so hard, but when it comes to some specific examples, like the mapping torus, especially when there are some quotient spaces involved, so it can be very complicated, and there will be some technicalities where you need to use some theories and some techniques, like cutting the space into some pieces using like Meyer-Vittorius sequences. And one more criteria. This example can be generalized to say higher dimensions or some more abstract constructions. And it can be used over and over again in deeper and deeper theories. So this is a fourth criterion. And I will show you the example that I'm going to give you on the isomorphism of two measure preserving systems. We'll have almost all of those criteria. And that is why I call that example very, very good. So now I will show you this example. This example is called the Bernoulli shift. And to be more rigorous, I should say this will be a special case for a Bernoulli shift. So we define the 1/2 measure, and we denote this measure by mu sub 1/2, 1/2 on the finite set 0, 1 as follows. Mu sub 1/2 of 0 and mu sub 1/2 1 to be both equal to 1/2. So you can think of this space as a discrete probability space. And this probability, as you know from the probability theory, has a Bernoulli distribution, like flipping a coin. And now we'll generalize this construction to infinite dimensions. Let x be equal to this 2-point space raised to the infinite dimension. So this will be a countable infinite product. And this notation means non-negative integers. And we equip this space with the infinite product measure. And we denote by mu equal to this infinite product of mu sub 1/2 1/2. And now I have to tell you what this space really is. First, what is the sigma algebra on it? And then, how is this mu really defined? So I only give a formal notation here, but I have to tell you the specific meaning of this. So first, what is the sigma algebra? The sigma algebra, B, is the Beroulli sigma algebra of the compact space 0, 1 with infinite product. So why do I call this compact? Why this compact? This is compact because this 2-point set itself is compact. You know that the product of compact sets is always compact, no matter this product is finite or not, by a so-called Tikhonov theorem. Okay, now what does the Beroulli sigma algebra of this space really look like? Let me make it more specific. This means B is generated by cylinder sets. So now I have to tell you the meaning of cylinder. By this I mean the set like this. You will have only finitely many non-full factors. So A sub i's are subsets of 0, 1 for I greater or equal to 0 less than or equal to a finite number m. And you take the product of A0 through Am, and starting from m plus 1's place, you will always use a full space. That is the meaning of the cylinder sets. Of course, so A sub i's are also allowed to be the full space. Say A0, A1 can be full, but A sub 2 can be just the singleton 0 or 1 or even empty set. And that is the meaning of the cylinder sets. And mu, how's mu defined? Mu of this particular cylinder set is just defined to be the finite product of Bernoulli measures on the first m plus 1 components. And you know that this product is nothing but the number of elements in there divided by 2, and you take the product. You know when A sub 0 through A sub m are all full space, this will be 1, because each term will be 1. And if they are all singletons, this will be 1 over 2 raised to the power m plus 1. It's like the probability that you flip the coin and get the heads for m plus n times. So I already said it, but let me emphasize. This space is a natural model for the set of all possible outcomes of the infinitely repeated toss of a fair coin. So this is a natural model for the coin flipping. Okay, now I just told you what Bernoulli is. Now I have to tell you what shift is in this example. And I forgot to label this. This is example 2.8 in the book. The shift is the following. We define the left shift map, denoted sigma from x to x, defined by the sigma applied to this infinite sequence is equal to the shift of the sequence to the left. It's like you are moving the sequence one step to the left. Well, depending on your culture, so in your culture you might call this the shift to the right. But anyway, you know what this means. You just remove this x0 and you move x1 to the place of x0 and x2 to the place of x1. That is what you get. The name left or right might be ambiguous depending on your cultural background. And now we claim that sigma preserves mu. Remember that this mu is defined to be the infinite product. Namely, mu is something like this. And recall that by measure theory, to verify this, it suffices to show that sigma preserves mu over cylinder sets. Because you know, the cylinder sets form a semi-algebra inside the Beroulli sigma algebra. And remember at the beginning that I mentioned the theorem 8.8 that to prove a map is measure preserving, it is necessary and sufficient to prove that it is measure preserving over a semi-algebra. And I suppose you can verify easily that the cylinder sets really form a semi-algebra. So empty set is in here, and if you take the intersection of those two, it's still in here, and if you take the complement, you'll be like a disjoint union of sets like this. It shouldn't be hard to see, because anyway, those are just finite terms. And so let's verify this over the cylinder sets. So now if you take a cylinder set and you prove this back by sigma, what do you get? What you get is the following. You get, instead of starting with A0, this time you will start with this whole space, and the second term is A0, and the third one is A1. Okay, now you start with the cylinder set, where at most the first n plus 1 terms could be not the full space. And now you apply sigma inverse to this infinite product. What do you get? What you get is the following. By the definition of this left shift map, what you're going to get is you will start with this whole space, and the second term you'll get A0, and third term A1, all the way to AM. And now you apply mu to here, to both sides. And this second term, the definition of mu will be just equal to the mu sub half first set times mu half of the second set, which is A0, all the way to mu half of the AM. And you know this guy is just equal to 1. So what you get in the end will be same as the mu of A0 times all the way to AM times 0, 1, all the way. This proves the measure preserving of sigma. Now you have a measure preserving system over X with respect to this left shift map. And now we'll look at this example in another way. We'll identify this measure preserving system with something that we have already seen before. And that is the complicated part, because in that part we're going to show that this system is isomorphic to a system we have seen before.